Hello students, welcome back. Let us resume our discussion in section 4, Riemann sum and Riemann integral. Previously, we went through the concept of partition, remember this? And then Riemann sum. Remember those? So given partition, we can consider rectangles like these, where y-coordinates are selected anywhere between the minimum and the maximum, and subinterval width becomes the width of these rectangles, and if you add those areas, then I'm going to get a rectangular approximation of a signed area, basically, if we have a graph. In this case, we see a graph, so it makes sense, but if the graph is completely undrawable, unvisualizable, then the signed area concept is invalid. We'll have to hold on to this because algebraically this one always makes sense. Now remember, in a special case, when your function is continuous, then you can replace yi star as f of xi star. Remember that too? Here's a visualization. In case of all those green rectangles, yeah, any y value between the minimum and maximum corresponds to a function value of something. If you have discontinuity, not necessarily, but the discontinuities will not cause too much trouble as long as there are only finite many. In this case, we have one discontinuity right here. So all I have to do is to consider one interval here to the left and another interval there in the right hand side. And we have two continuous functions, one here and one there. And then one here we have Riemann sum of say 5,000 intervals. And then the other one here we can consider a Riemann sum of 2,000 intervals. And then I can add them all up and we get a Riemann sum of 7,000 intervals from here to there. No problem. If you have 15 discontinuities, then I'm going to get 16 continuous pieces in 16 intervals. So we can consider Riemann sum separately, all 16 of them, and then I can add them all up. If there are infinitely many discontinuities, now we do have indeed a problem, and that's not something we are going to do here in 1,000 level course, or even 2,000 level course, or even 3,000 level. That's way up there. We are going to do those in some 4,000 level real analysis course. So, moral of the story, even if you have discontinuity, no problem. You can always cut those and then consider continuous pieces, piece by piece. So we can reduce arbitrary Riemann sum into f of xi star as if everything is continuous 90% of the time or 99% of the time. Not always, but most of the time. And that's the kind of Riemann sum we're going to consider. This one here, considered by our textbook author, is a bit too specific in my taste. Just evenly spaced intervals only, and that causes some problem, especially if you have discontinuity that can come anywhere, and then if you consider evenly spaced, then there's no guarantee that that one of those partitions will hit this discontinuity directly, so that we have continuous piece here and there, we'll have some mess. So I don't like this expression very much unless we have a nice, very nice continuous function and we are doing a numerical approximation. In terms of theory, I like this one a lot better, so I'll stick to this. In other words, we are going to step a little bit ahead of our textbook. So we are going a little bit more advanced. Okay. So much for all those review and preparations, and I think that's time well spent because we are doing something really hard. Okay, finally, let's go over to Riemann integral. Here's the definition. The limit of Riemann sum for all partitions, all Riemann sums, where the interval size go down to 0. Let's see. The subinterval size delta x going down to 0, what does that mean? What is delta x? That's a maximum. So maximum is going down to 0. That means everything is going down to 0. All delta xi's, they're all going down to 0. In other words, all those rectangles will become infinitesimally thin and go down to zero. Let me see. Is there a visualization? Let's use the same visualization I showed you before. Here, instead of 20 rectangles here, let me use 200. You see a little bit better approximation? You still see some fat rectangles here and there because of this is pretty random. And then that means this is worst possible case. Yeah, even if I run many times, approximation is still pretty bad. We have all those fat rectangle. But if I just go ahead with even more rectangles, yeah, this is a typical situation you're going to get. And look at these. The Riemann sum computation and the integral turning out to be pretty much the same. And that's the worst possible case. Things like this, in terms of computation, this is going to be far more effective. 10 rectangles here, if I go to about 50 rectangles, already the approximation is pretty good. But then again, these may be good for computation. For theory, it's not very good because, you see, in terms of theory, you want to show that this integral exists. In other words, the limit must exist. How do you know the limit exists? The rule that you can use is a kind of sandwich rule, the pinching rule. The worst possible case, biggest versus worst possible case, the smallest. And even those merge together into the same value so that everything goes to the same value. If that happens, then the limit exists for all Riemann sums, and consequently this quantity is well defined. And in that case, we say your function is Riemann integrable, and this quantity here, and the common limit value is called Riemann integral. And the definition of Riemann integral is, as you see over here, the limit of Riemann sum, all Riemann sums, any Riemann sum, where the subinterval side delta x is going down to 0. Now, subinterval side delta x going down to 0, does it mean the number of intervals n going to infinity? The answer is yes, of course. I mean, the interval width are going down to 0, very close to 0, then in order to cover an entire interval a to b, you're going to need numerous intervals like that. So if delta x goes to 0, then n certainly goes to infinity. But not vice versa. N going to infinity does not necessarily mean delta x going down to 0 for uneven intervals, you see. You may have some gazillions of points here and also there, and you can keep this red one the same so that delta x does not go down to 0. You can consider those kind of arbitrary examples. You see, in order to have something defined and prove that it is well defined, you have to consider the worst possible cases. Like Murphy's law, everything that can go bad will go bad if you have to consider that. But for evenly spaced Riemann sums, if the delta x, the interval size is all identical, which is the same as b minus a over n, the original interval length, b minus a, divided by n, evenly divided. In this case, this one, b minus a over n going to 0, and n going to infinity mean the same thing. So in our textbook, the limit is written as n going to infinity, but that's too specific. You see, if you have something like this, then you can rewrite this limit as n going to infinity. And this is how the definite integral is expressed in our textbook. But that's so 1000 level, or okay, all right. This is 1000 level course after all, but that's in my opinion too specific. That's how you can define. That's how you should define. So it should work for any Riemann sum, not just evenly spaced Riemann sum, but for any Riemann sum. So if that limit exists, then we say the function is Riemann integrable in that interval, and the common limit value is Riemann integral. By the way, the Riemann integral, that's the same as the definite integral, and there are other ways to define definite integrals, but they're all really, really advanced, probably in graduate level. So at this moment, Riemann integral and definite integral are the same. Okay, we went through the definition of Riemann integral finally. Do you have time for an exercise? Let's try. Express the given picture as a Riemann sum in this interval, and what's the picture? Okay, like this. All right. So, function values f of -2, f of +2, f of 6, and f of 10, those are height. And what are the width of the rectangle? -4 to 0, so that's width 4, and 0 to 4, again width 4, 4 to 8, again width 4, 8 to 12, again width 4. You can express it like this. Width times height. Width is 4 for each of those, and the height of f of -2 right here, and f of +2 here, and f of 6 here, and f of 10 here. So sum of these 4 rectangles. Does it make sense? Okay, now that you saw an example, do this one on your own. Stop the playback and do this one on your own. Did you get it? What's the interval width? -4 to 0, 0 to 4, 4 to 8, 8 to 12. Okay, all right, width is 4 all the way. How about the height? What is this height? F of -4, f of 0, f of 4, and finally f of 8. Do you see that? Make sense? This is left-hand side Riemann sum. Previously, it was midpoint Riemann sum. Okay, final example here. Again, stop the playback and do it on your own. This time you have uneven interval width. Did you get it? You have 4 rectangles, so you have to add 4 quantities. First one has width of 1 unit. The second rectangle has 3 units. No, excuse me, 1, 2, 3, 4, 5 units all the way up to here. I accidentally looked at this coordinate axis. No, actually interval begin from here to over there, so 5 units. And then the third rectangle, how many units? 7, width is 7. And then final fourth rectangle has width of 3 units. And what are the heights? F of -4, f of -2, f of 5, and f of 10 respectively. Make sense? Resulting in this quantity. Make sense? That's how you can express a Riemann sum.